Hello and welcome to this video where we'll be looking at elements and isotopes. So first question is, what is an element? Well, by definition, an element contains only one type of atom. So pure gold only contains gold atoms, pure oxygen only contains oxygen atoms, and so on. The different atoms mean that elements have different properties. For example, gold is a soft, shiny metal, whereas oxygen is a colourless gas. Here's a periodic table. We looked at this before. There are over 100 different elements in the periodic table. We're now probably about 115, so it's getting bigger by the day. Now each element in the periodic table has a unique symbol consisting of one or two letters. The first letter is always uppercase. For example, the symbol for hydrogen is H. You can see elsewhere here we've got potassium. Over here we've got boron and carbon and nitrogen. So some elements have just one letter and it's a capital. Now if there's a second letter, it's always lowercase. For example, lithium is capital L, lowercase I. You can see it again with beryllium, capital B, lowercase e, and so on. Now you do not need to memorise all symbols in the periodic table, but it would be helpful if you could learn the first 20, from hydrogen here to calcium here. So looking at hydrogen, helium, lithium, beryllium, and so on. Now most symbols in the periodic table are obvious, H for hydrogen, Li for lithium, but sometimes symbols are based on Latin or Greek. For example, here we've got lead, Pb. What's that about? Well, Pb, lead, the original Latin or Greek was plumbite, which is where we get Pb from. Let's look now at mixtures and compounds. A mixture consists of different types of atoms that are not chemically bonded. In this example, we've got iron, Fe, and sulfur. Now, Fe and sulfur are entirely separate. They are not chemically combined together. The properties of a mixture are as follows. Firstly, particles in the mixture can all be separated out quite easily. For example, iron and sulfur, by using a magnet, we can separate the iron from the sulfur. No chemical bonds exist between the atoms, and the properties of the mixture are just a mixture of the properties of the separate parts. So here it's partly magnetic because of Fe. In a compound, the particles are held together by strong forces called chemical bonds, and in this case a chemical reaction will have taken place. We've now got iron sulfide, and there's iron sulfide. Here's carbon dioxide. In terms of properties, particles in a compound are very difficult to separate. The properties of a compound are very different to the properties of the original elements. So here, even though we've got iron sulfide is no longer magnetic. You can't separate the two using a magnet. In the periodic table, the individual elements are placed, as we learned earlier, in order of increasing atomic number. And here we can see a block of these. We've got boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, and neon 10. Now for every element in the periodic table, there are two numbers associated with it. So here we've got, for example, magnesium. Magnesium has got a mass number 24 and an atomic or proton number of 12. Some elements, such as chlorine, have rather odd looking mass numbers. Look at this, 35.5. How can you have half a proton or half a neutron? Well, you can't. These odd looking mass numbers can be explained by the existence of what's called isotopes. Isotopes are different forms of the same element which have the same number of protons but a different number of neutrons. So here we've got chlorine, got 17 protons, but we'll see in a moment the isotopes have different numbers of neutrons. So isotopes have the same atomic number but different mass numbers. Chlorine, as an example, has two stable isotopes, chlorine 35 and chlorine 37. For every one atom of chlorine 37, there are 3 atoms of chlorine 35. So to work out the average, we have a 37 here, 35, 35, 35, because they're 3 to 1, aren't they? Makes 142. 1 and 3 makes 4. That gives us an average of 35.5, which is where our number comes from. Other examples of isotopes, we've got carbon 12 here, which is normal carbon, and we've got carbon 14 over here, and they differ in that carbon 14 has 2 extra neutrons. Many elements exist as a number of different isotopes. The average mass takes into account the different masses and the abundances of all the isotopes that make up the element. We refer to this as the relative atomic mass, or A, with a little subscript R next to it. To calculate relative atomic mass, we look at this equation. The sum of isotope abundances times isotope mass number divided by the sum of abundances of all the isotopes. That seems rather complex and difficult to get your head around. Let's look at an example of that. Let's look at an example using copper. This is copper 63, which is abundant in 69.2% of all atoms, and copper 65, all atoms of this are 30.8 in terms of abundance. Here's the equation we had before. Let's now put the figures into it. We've got 69.2, which is the abundance of copper 63, times 63, plus 30.8, the abundance of copper 65, times 65, divided by the sum of the abundances, which is 69.2 plus 30.8, equals 4,359 plus 2,002 divided by 100, which equals 6361.6 divided by 100, which equals 63.616, or to round it up a little bit, 63.6. Okay, and that's the relative atomic mass of copper, taking into account all of its isotopes. Okay, hope that's made it clear. So thanks for watching and listening, and we'll be back in the video very soon. So bye bye for now.